my marker already. Okay. Here we go. We're going to look at how to balance chemical equations in this. So I'll put that up here. Balancing chemical equations. The first thing we need to know is about the law of conservation of matter. Oh, what is that? Wow. I'm going to rewrite that because this is a struggle. Conservation of matter. All this, the law of conservation of matter, conservation means like keeping, right? Saving. It just means that we can't create or destroy matter in chemical reactions. It's always going to go someplace. So basically what the amount of matter you put in to a chemical reaction should come back out. You may not always be able to find it. Here's the problem. Like burning wood, like a campfire, is a chemical reaction. If you throw a whole log in there and wait a couple hours, you don't find the mass for a whole log. It went somewhere. Right? Rose up as smoke and it's gone. It's out in the atmosphere. You know, eventually it'll come back down. But we change what form it's in. Right? Burning a piece of wood, we started out as wood, then we changed it to smoke. We changed it to CO2 and water, and there's some smoke, little particulates that go everywhere, and there's some ash that didn't burn on the ground. But that's what we're doing with conservation of matter. If we collected all that smoke and CO2 and water that burned from that piece of wood, we would have the same amount of mass. We could count it all together. So balancing chemical equations keeps us from violating that rule. The other reason we can balance chemical equations, it gives us a ratio. Like this is something that has to be true all the time. But when we balance, I'm going to write this here. Balancing equations gives a ratio of products. Oh, I want reactants to products. Reactants to product. So let's say we're working as chemists in a lab and we're trying to make chemicals. Like we work for some big company and they want us to produce hydrochloric acid. We need to know how much hydrogen and chlorine we're putting in there and then what we should get out. You don't want to waste extra hydrogen than your put in more hydrogen than chlorine, like what you need to get the product out, because then you waste money on product or on reactants, on things you're going to put in, and you don't get enough product out. They also use this to check their work. If you're a chemist working out in the field, right, making chemicals for somebody, you can check your work to see what you would expect to get out versus what you're putting in and see if there's something going wrong in your chemical reactions. So it's super helpful for people working in those fields, right? It's a way to check their work to make sure their productivity is high enough. Because if you're doing a chemical reaction where you're putting a lot of stuff in and getting very little product out, you're not going to make money. Right? Think about it on something we're probably more familiar with. If we took a whole tree and we want to make toothpicks, out of that tree, with cutting down one tree, shaving it all the way down to one toothpick, would that be productive? Would you make money that way? No, you're going to want to shave that tree down to billions of toothpicks, right? Or millions or whatever, how big that tree is. But you want to get as many toothpicks out of that one tree as possible. Same idea with chemical reactions. Balancing helps us figure out all that stuff that we're doing with our chemical reactions. So our next thing we should probably look at is what's a reactant and what's a product. We're going to put a chemical reaction up here. Let's do something. I have a list of things. I'm going to choose something. There we go. So how about this one? Na. So we have sodium plus oxygen, and that's going to give us this, Na2O, sodium oxide. I left kind of big spaces. I'm going to put these blanks in here. We're going to have to balance this, but our first thing I want to look for and define is our reactants and products. Remember, so that one. So over here, we have reactants. Reactants. There we go. And over here we have product. These are what we're putting in to react together to form something else, right? These are reacting to produce. Our arrow tells us which way our equation's working. So we know we're mixing these, producing this. If we flipped our arrow around, if we had something like this, which it can't happen in chemistry, we're not going to see it. This is now our reactant and this is our product. So we got to be careful which way our arrow's pointing. I'm always going to keep them pointing in one direction. When you get to high level chemistry, then the arrows point different directions and they get all weird. Ours are just going to point to the right. So we should always have reactants on the left, products on the right. Okay. So let's look at our equation here that we have, because this is not balanced. We don't know how much sodium to oxygen we should put in there. We know those are what we're going to put in, and we're going to get sodium oxide out. We just don't know how much sodium, how much oxygen to put in. Right? We don't have that ratio. So we're going to balance that. So what I'm going to do, underneath, I'm going to make a table. I'm going to count my sodiums on the left side and my sodiums on the right. My oxygens on the left and my oxygen on the right. So I'm going to make a little table of the elements I see. So I have sodium, my Na, and my oxygen. My table on the right is going to look the exact same way. So I have Na and O. So before I start trying to balance anything fun, I'm just going to take and count my sodiums here. There's no little number after, so I have 1. My oxygen, there's a 2 after, it says there's 2 oxygens, so there's 2. Come over here, I have Na, the little 2, so I have 2 sodiums. My oxygen has nothing after, so it's a 1. And we can look at this equation and go, look, we have 1 sodium over here, but 2 over here. So we reacted stuff together to get extra sodiums. Can't create or destroy matter, so we have to put more sodium in. So I put this thing here. We'll label this as a coefficient. All it's saying is we're going to put more of this in. We're going to put 2 times the sodium in. So we're just multiplying this by 2. So our sodium is now multiplied by 2 on this side, which means I put 2 sodiums in for every oxygen now. It comes out balanced, right? 2 and 2. Okay. my oxygens are not balanced, right? I have one here, two here. That doesn't work. I need more on that product side, right? This would mean that I lost oxygen, it just disappeared. Can't destroy it, has to go somewhere. So I'm going to put a 2 here. This is distributive, so I have to go 2 times my oxygen and 2 times my sodium. So let's do oxygen first, because that's what we're looking for. So now my oxygen is now 2. I have 2 times my sodium, so I have Na2, but I have 2 of them. So now I have 4 here. Oh. But my oxygens are happy, right? So I have to come back to this side. This coefficient doesn't work for me, because I have 2 sodiums here. They're unbalanced. But if I put a 4 here, 4 times that 1 gives me 4. Now they're balanced. We don't need all this here. So now my balanced chemical equation looks like this, where we have 4 sodium for every oxygen, gives me 2 sodium oxides. We don't need to put a 1 here just by having that O2. We assume there's a 1. If you want to put a 1, you can. It's not wrong, but you don't need it. You can just leave it blank. Okay. Should we try another one? Yeah! All right. I'm going to give us a harder one. Or a similar one. I don't know. I'm pulling them off a sheet. I haven't done them either. Don't have the answer key yet. Let's try this one. So we have C plus, I'm going to put blanks, S, 8 gives me CS2. First thing I do is I start with my table. I have C and S. Make it on that side too. I like dividing it so I see where the left and right sides are. C and S. I'm going to count my carbons. I have 1 S, I have 8. Over here I have 1 C, S is 2. Carbons are happy, so I'm going to leave those alone. S, I have 8 over here, 2 over here. This side needs to go up. So I can ask myself, what times 2 gives me 8? So 4 times 2 is 8. Right, so I have 8 here. But remember, it's distributive, so I have 4 times the 2. And I also have 4 times that carbon, which is a 1, so this now becomes a 4. I always update my table as I go. That way I can see where I'm at and keep track of things. Because now I know my carbon over here is not equal. I need it to be a 4. So I'm going to put a 4 there, which is 4 times 1. Balanced. Yay! I'm going to try another one. Ready? Let's try this one. So C3H8. Yeah. So this, I believe, is propane. So we're going to burn propane with, what is this? Burn propane with oxygen, and we should get CO2 and water produced. So again, I'm going to start by dividing where my arrow is. I'm going to make a table for everything I see. I have CHO. So CHO. Make another table over here. CHO. Got our tables. Best place to start. I've been teaching this for years and I still do it this way. I still make tables for new ones when I'm lost in keeping track of stuff. I can't do it quickly in my head. Make a table. So I'm going to start with what I have. I'm going to switch colors on this one too. So C, I have 3 carbons. Hydrogens, I have 8. Oxygens, I have 2. Right? 3, 8, and 2. Same thing here. Carbon, I have 1. Oxygen, I have 2 here. I also have 1 here. So I end up with 3. So right, 2 plus the 1 gives me 3. Hydrogens, only in one place, there's 2. I'm going to switch colors so then you can see where I'm putting stuff in as I change. One bit of advice, if things are near by themselves, like O2, I do it last. So I'm going to save oxygen for the end.
Hey. I have a question for you.
Okay.
Okay, so Zach is putting on a possible City Hawkins in. Can we come in, or are you just gonna walk?
Okay, so now back to this interruption thing. Okay, we start here, right? Carbons, I have 3 here, 1 here. I obviously need more on this side. So what times 1 gives me 3? Hopefully we got that. And I'm going to update my table. I'm going to change that to a 3. If you're doing in pen, pencil, just cross out and change the number, right? Oh, distributive, right? So my carbon also goes up by 3. My oxygens also are now multiplied by 3. So I have 3 times 2 plus this oxygen here. I'm going to write it up on top so I can see it and keep track of myself as I go. Right, so I have 6 plus 1, so I have 7 oxygens. It's important to update your table with everything as you're going, otherwise you'll lose track of things. Real quick. I'm going to do hydrogen next. I have 8 on the left. I only have 2 over here, so I need more, right? Multiply that by 4 to get me to 8. Because 2 times 4 is 8. But now I also have this 1 times 4. My oxygens need updated now. So I have 6 here, 4 here, so I have 10 oxygens. Yay, this one comes out nice. So I put right, I need something times 2 to give me 10. I need 10 down here. So if I put a 5 in there, 5 times 2 gives me 10. Works out. Yay! I hope you got that one too as we're working along. Ready to make it gross and harder? We're going to change very little on this. We're going to do the same concept here. Revert back to my table. Fix this out. I'm still going to burn something. I'm going to take C6 and 14. This is gasoline. This is hexane. So we have gasoline. We're going to burn it with oxygen, get CO2 and water. I'm hoping you pause here and try this one on your own, because I'm going to work it out in just a second. Paused. See that? Yeah. Alright, so I'm going to start balancing this. So I have 6, I have 14 here, and 2. I have 1 hydrogen, there's 2. 2 plus the 1, so I have 3 carbon again. Just like our previous one. I'm going to switch again to my green so you can see where I'm updating stuff. I'm going to start with carbon. I'm going to save oxygen for last because it's by itself. So my C, I have 6 over here times 1, right? So I have 6 there. 6 times 2 We did this last time, so I'm going to do it again. And then we have 1 over there. So we have 6 times 2, giving me 12, right? Plus the 1 gives me 13. We got some. Let's do hydrogen next. I have 14 over here. Need some more over here. 7, right? 7 times 2 gives me 14. But I also have to update this, right? 1 times 7. So we have 7 plus 12 gives me 19. Oop. 19 now. So what times 2 gives me 19? Didn't mention this before, but we have to have whole numbers. Because I could put in here 9.5, right? Because 9 times 2 is 18. Half, 2 halves is a whole, right? I can't have that. Because that would give me 19, right? Problem is I can't have half of the molecule. I can't just like, nah, you're gone. So we have to fix that. The easiest way to get rid of a half is to multiply, I'm going to simplify this down, everything by 2. So I'm just going to distribute that 2 into every spot, right? I'm going to take 2 times here, times here, times here, and times here. All those numbers. So 2 times 1, 9.5 times 2, that already gave us 19, right? 6 times 2 is 12, and 14 here. So let's check our math, make sure everything balanced. 2 times 6 is 12. 2 times 14 is 28. 19 times 2, 38. 12 times 1 gives me 12. 12 times 2, I'm going to write it here because I also have 14 times 1. So we have 24 plus 14 gives me 38 oxygens. 14 times 2 gives me 28. Do all of our red numbers match? Yay! I love it when it works out. This is the hardest problem you're going to see, is something like that. I hope this helps.